and I'm just remembering how it works. So the first part didn't work. Any questions about the homework that's due by midnight tonight-ish? Okay.
So there wasn't any real answer in what we read. We just had to draw our own conclusion.
Yes. Yeah. Very. What's that? You did.
I think I may have done it wrong.
Oh, that's fine. You'll see that along with not being an English teacher, I'm kind of when it comes to homework, kind of flexible to how you answer it, other than you need to answer it with your own words and such. So I'm sure you did fine, Courtney. Oops, that isn't right. My goodness gracious.
Those were the questions about like astrology, right?
They were. Yep, you got it. Yep. Oh well. Okay, let's do it this way. Do y'all have any questions about Canvas? Are you finding your way around Canvas okay, or whatever? All right. Good. All right. So the way lecture goes, I think I might have mentioned this on Wednesday, was anytime you see a slide that has this border around it, that is a slide that I got directly from OpenStax. A little bit ago, I stood up here and I went like this. What was that?
Galaxy.
The galaxy. What do you think? Galaxy. I'm gonna dim some lights. It's just too bright in here. Sorry. Just let me know if the dimming the lights is bad. Much better. Yep. So this is what we call a face-on galaxy, or a view of a face-on galaxy. What's at the center of the Milky Way galaxy? A black hole. Very good, black hole. There are little black holes and there are big black holes. It's a supermassive black hole. We actually think that there's a supermassive black hole in the center of most galaxies. It kind of had to be there for them to form. Does it look like there's multiple galaxies here? Yeah. Galaxies, and it's a gravity thing, actually kind of fall together sometimes. They're drawn together. Our galaxy, the Milky Way galaxy, is actually doing a dance and being drawn towards the Andromeda galaxy. So yeah, that's going to be a big hairy deal in, I don't know, maybe a couple million years. So, something to look forward to. So this, I'm going to click on this link up here. So anytime you see an underlying thing, that's going to take us out to a video. Let's see. Oh, see, and my thing doesn't work now because here. So if we go back to the slides, basically what that video talked about is what's on this first slide. Okay. Do you guys remember, what did the slide say with regard to Neptune? How many AUs is Neptune away? Do you remember? 30, yeah. 30.1, you guys got it. One of the things I like about this video is it emphasized that we are seeing, so when we finally see light from the Andromeda galaxy, it left it 2.5 million years ago. That's one of the reasons it's just kind of humbling. And the other thing is I get excited because I'm like, dude, it took all that time for it to, if we're looking through a telescope or binoculars, for it to be gathered, condensed. I see it, I recognize it, and it's gone. You know what I'm saying? So do you think that Andromeda Galaxy has aged? Do you think it's aged since 2.5 million years? Yeah. So that's kind of one of the things we combat when we look at things from that kind of sky. So I'm not going to do this, but just kind of a thought exercise. So one of the things, I'll give a little bit of light, I'm going to go back and forth just because I can. You guys are stuck in your chairs. I can go back and forth. One of the things we need to be able to do is, and it's not really math, but we need to be able to pack up big numbers more likely than small numbers. Some of you guys are already familiar with the scientific notation thing, and that's what I'm going to show you. So for instance, there are way too many zeros for this number, okay? And for the second number, it's a really small number, there are way too many kind of what we call leading zeros there. So if you're not familiar, I'm going to kind of talk you through it. Let me grab my pen. So what I do, and I'm not a math teacher, I'm not an English teacher, so that rules out those two things. But what I like to do is I find the decimal and I move it over so I have a number between 1 and 10. So for this first one, where is the decimal in this first big number? The decimal is kind of implied way over here. That's kind of where the decimal is. Does that make sense? Because like if I was going to do 0.1, like this kilometer is 0.1, I put the decimal and I put a 1 there. Does that make sense? Or 0.50, I put decimal 0.50. So the decimal's kind of, if it's a big number, kind of way over at, I get my left and right mixed up too, way over at the right. So now I'm going to move the decimal to get a number between 1 and 10. And in this case, I'm going to move it to the left. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I put the decimal, maybe this is what you were saying, but if I put the decimal right here between the 1 and the 2, I'm going to have 1.23. And in scientific notation then, I put times 10 raised to the however many places I had to move it. So what I get, 9, 10? Okay. Okay, I'm going to put 10, and it's actually going to be a positive 10 because it's a big number, and I've had to move the decimal to the left. Okay, I feel like I need to mention that because when we deal in astronomy with some big numbers, we're going to see it packed up like that, and I don't know what that is. Less likely we're going to see the small numbers, and it looks like this. Now, in the case of this one down here, I go 1, 2, 3, 4, 5, 6, 7, 8. I got 9. And my decimal number is going to be 4.721 times 10. And now it's not going to be just 9, it's going to be negative 9 because it's a small number and I had to move it over to the right. That's a negative 9 up there.
You move over until you're no longer in the zeros. That's what you're supposed to do.
Yes, you move it over so you're no longer in the zeros. That first digit. Yep, you got it. Either one, yeah.
Yeah, but I can't. Not so long ago.
I think, what would you say if I had two objects, one was 1.23 times 10 to the 10th kilometers away, and one was 1.23 times 10 to the 56th kilometers away, okay? Which one would be farther away? The one times 10 to 56. And I kind of wanted to that's what I wanted for you guys to know. So if I wanted to make that, what I say, unpack from 1.23 times 10 to 56, I would have to I would take my decimal place and move it over 56 places and then fill in zeros. You'd be like, hey, Graham. So that's kind of what I'm after more than anything. I think I've got an example. So I'm going to give you just a few. And you get to, you guys, oh, you don't have the slide. So let's do these, because if you didn't print them out, right? Let's pick a few. How about somebody help me?
We already did the first one.
Oh, well, there you go. We already did these two. Thank you. What about the bottom one down there? What do you think? How many places do I move the decimal over? Oh, I had 4. I heard 4 and 5, and actually 5 is the right number because I have to keep moving it until the numbers between was less than 10. Okay, so it's times 10 to the 5th. What is my decimal number? 1.01. You got it. Let's not worry about the small ones. Let's go for this one. Okay, so what do you think? How many places do I need to move it over? 3, 6, 9, 10, 11. I'm getting 11 because I got 3, 6, 9, and then 10, 11. So there's 9 here and 2 here. I know it's hard. What's that? Mm-hmm. Yeah, we can't stop at the commons. If we stopped here at 9, our decimal number would be 591.45. And that won't work because it has to be less than 10. So we had to keep going 2 more places. Yep.
So it always has to be less than 10.
It always has to be less than 10. They call that the coefficient, that decimal part. Yep. So we're going with, you guys told me 11 places, and then the decimal number would be 5.9145. Okay? Now, I don't mean to scare you all off, because like this class, I don't do any of the math. And some of my peers who teach Intro to Astronomy are like, how could you not do any math in Intro to Astronomy? But I don't.
Sign up for this class for the math.
I know, right?
Sign up for the stars.
Right. So let's do this little cosmic voyage video. The thing about this that tries to kind of put in perspective with regard to astronomy what 1 factor of 10 is. So we can kind of think about this. So if I go 1 foot, I go that much, right? Okay. Oh, I wore my astronomy shoes today. And if I go 10 feet, I go this much. Right? Maybe here-ish. If I go 100 feet, I'll be walking a lot. If I go 1,000 feet, and all I'm doing is just kind of adding a 0. So it's the powers of 10. Yeah, at some point it'd be let's work. I'd much rather be here. So it'd be powers of 10. All right. And I feel like we've kind of talked a little bit about this idea. We measure things in light years. Did you catch the video we watched? Said that I liked the animation. It showed light starting from a star, and it takes a certain amount of time for light to get from point A to point B. Now, we're really bad about when I flick on the light switch, you're like, dude, turns on, it's here, just like that. But there is a delay. And so, like, for instance, from the moon, it takes the light 1 second to get here. From the sun, it takes the light 8 minutes to get here. From I think you even mentioned the star Sirius, about 8 years. And Sirius is the dog star. If you can find Orion, the constellation Orion, we'll be seeing some pictures of the constellation Orion. Orion's got kind of a body to him, and then he's got like a belt, and then he's got a sword hanging, just so cool. Anyway, he's got a dog, and the dog is Sirius, or dog is Canis Major, Andromeda Galaxy. So it makes things a little tricky. You don't need to know these, but do you see why I kind of wanted to do a little bit of scientific notation? So which of these is the farthest away in kilometers? Andromeda Galaxy. Because I wanted you guys to have a sense for, what is this 10 to the 19th? Why? What the heck? Well, that means if I were going to unpack this number, I would take that decimal and move it over 19 places. That's one heck of a number. Okay? There was a movie, and now it's kind of an old movie, but it was based around Alpha Centauri, one of the planets around Alpha Centauri. By the way, is this right? Man, there's been a lot of planet activity going on out there. We call those extrasolar planets. So they're not planets around our sun, but planets around other stars. But anyway, our closest star is about 4.4 light years away. Okay. Again, one more thing about the close by star. Another thing that's been in the news, and I think these are just like college students or something that have, or high school students maybe, they've come up with little gizmos to not put in orbit around the Earth, but basically send them into outer space to stars. Like, why not, right? So anyway, it's kind of cool. So when we're looking at things, we're looking at as they were a long time ago. So if we're looking at the sun, actually we're looking at the sun as it was 8 minutes ago. If the sun were just to go away, it would take 8 minutes for us to know it was gone. If the Andromeda Galaxy were to go away, it would take 2.5 million years for us to know it was gone. One of the things astronomers, amateur and otherwise, get excited about are when a star blows up. Anybody know what we call that? A supernova. When a star blows up. We get excited about that. But you figure it happened a long time ago by the time we finally see it. So that region gets bright for about 2 weeks and then kind of it goes away. So we're looking at old light. This is, maybe you've seen this before, and if you come out to the Whitty Observatory, you're going to see we've got 2 domes. This is a dome that houses a telescope. It's got a little slit here where when it's clear and we want to look out, we just open up that slit, and then this round thing up here, it rolls around. So if what we want to see is over here, we take the slit and we move it around. So that's a dome that houses a telescope. The point here is that the folks in here in the telescope are looking at a couple different objects. One of the things, these are both galaxies, okay? Kind of the left one and the right one are both galaxies. When we look at farther away galaxies, they look more, honestly, the word is disturbed. Doesn't this galaxy look disturbed? Yeah. It's an older galaxy because the farther away we look at things, the longer the light took to get to us. Okay, so this is a picture. It's an older picture, but it's a younger picture. How does that work? It's a picture as that galaxy was, in this case, 12 billion years ago. This closer galaxy picture, as the galaxy was 7 billion years ago. Okay, in here, and not till like Unit 5, we're going to talk about the beginning, the origins of our universe, as all the evidence suggests. The beginning of our universe, which universe contains galaxies and galaxies contain stars. So actually it's a little more funner than that. I would say complicated, but it's more fun than that. Our universe contains something awesome called space. Like we take for granted, I'm walking around here. Okay, walking around space. That didn't exist before the Big Bang. Time, we take for granted time, you know, the whole Chronos thing. That didn't exist before the Big Bang either. So there gets to be a point where, kind of see this fuzzy region, and I think the video talked about the observable universe. There gets to be a point where you are looking far enough away that the universe hasn't been around long enough to basically send you anything because it's that far away. So we call that the cosmological horizon, kind of the edge of what we can see. We date the Big Bang, the beginning of our universe, the beginning of our stuff, the beginnings of our, what was going to be our stuff, the beginnings of our space and time about 14 billion years ago. So about 14 billion light years, that's when you bump up against that edge. So if you have your little, this thing, this is nice. Remember that each, here, just put it away. Each month, there's going to be a different one, and they slightly change. One of the things I like is if you flip it over, which, by the way, I swear I told you to do two-sided, and this is what I get. So anyway, usually you'll flip it over, and on the back side, it will tell you some things about kind of it. It basically is 3 categories. One you can see with the naked eye, this one you can see through a telescope, and this one, or this is my binocular, this one you can see through a telescope. So if we kind of peruse there, you might see the first M I see is M31. M31, I see M3, M13, M92. Those M's are Messier objects. Okay? And I'm going to think I'm going to go ahead and show you this video. It's about the right amount of time. But I brought this poster, and I'll leave it up in case you want to kind of come peruse it. But on this poster, you would find a little square that represents these Messier, these M numbers. Okay, and they kind of fall into some categories. They're either globular clusters, or open clusters, or nebula, or the last one would be galaxies. So let's check this out.
You don't want to know. Okay, well, good. You don't want.
Well, actually, I can see this one's a little bit longer than I wanted to go. So let's just end for the day, if that's okay with you. And we'll pick up with these couple of videos. We're almost done with part 2, but we'll knock out part 2 and begin part 3 on Monday. Okay? Okay. Actually, that clock is slow. It's about time. Okay. So my point is, you're free.